I would say we wait like 2 or 3 more minutes for people to join.
Right. So like five, we want to start.
Yeah, maybe just some minutes for people. Maybe they have meetings until 5, and then you can grab a drink and see it. I would say let's start.
All right. So,
okay.
Hello everyone. My name is Tu from community team of Saigon. So today I'm gonna be your host of MFQ Talk. Our guest speaker today is Jan Moser. I don't know if I pronounced that right. Our senior technical architect, and he will share with us the topic about the common software architecture patterns. So it's your stage, Jan.
Okay, thanks a lot. Welcome everyone, and thanks a lot that you take your time for this speech. It will be about common software architecture patterns, but it will also be like about ways how to get to an architecture. First, I would like to introduce myself shortly. My name is Jan Moser. As said, I work for Cohesion now around a year. I'm mostly living in Vietnam at the moment because of a customer. I'm 6 months or was 6 months in Europe. So I'm a international software architectural board instructor, an ISAQB instructor, and I'm also a certified Azure solution architect on the cloud world. I'm a Microsoft kid. I come from the Microsoft world, and when I do not work, I often do DJ in some clubs around Vietnam or Southeast Asia or the world, or go fighting in a Muay Thai ring. So let's start. Software architecture. First, we want to talk about software architecture, but first we need to define what is software architecture. There are many definitions of what software architecture is or should be. So I and also the people from ISAQB, we are sticking to this IEEE standard, or in Germany, DIN, Deutsche Industrienorm. And this standard says software architecture is the basic organization of a system represented by its components, their interactions and relations to each other, as well as the principles that are responsible for their design and evolution. That sounds very dry and very complicated, but it includes a lot of what it should be in the end. The software architecture basically is we are talking about systems. They are organized in some ways. We need to see how should a system be organized. We need to know first what is in that system. We need to know its components. We need to define the components. And then we need to organize them and form a big picture of what the system should be. These components, they interact with each other. They are related to each other. And we also need to define this. And at the end, because all that work requires some principles and guidelines for the developers, for the UX people in the end to do that, we need to have those principles defined. Mostly, or in the best case, before we start working, there can also be parts when we say we start at a certain point, but the best would be, of course, before we start working. And if we have those principles defined and we know where our stuff should be, how it should work together, and how it forms one big system, which does the customer's part, then this is what software architecture should be. In case there are questions, please feel free always to ask or interrupt. If after some slides, I also will repeatedly ask if there are questions to a certain topic. So, as software architects, our biggest goal should be high cohesion, low coupling. What do we mean with this? As you can see here in this image. Just a second, need my laser pointer. Here, we try to create a high cohesion. How do we do that? Cohesion means stuff that belongs together should stick together. That means if we have the software organization, the software system, and we have different components, we need to cut the system into stuff that belongs together. Imagine you have a web shop. In a web shop, you have maybe payment, you have topics which are orders, you have topics which are maybe products, all that stuff. And what you want to try is in Cohesion, you try to keep those order items, those payment items as nearly together as you can to create a high cohesion. That's the first thing. The second thing is we want a low coupling or a loose coupling. That means if the order and the payment needs to work together, we don't want to say, hey, please call me this explicit class and I need this like this. So you go here and say, hey, no, we want to loose couple. That can be either done if you use a contract-based interaction, be it, for instance, a interface, which you use both, and then you use something like dependency injection for that, because basically then both classes do not know each other. They only know the given contract. One supplies it, and the DI as a dependency injection or event aggregation or service provider component. So both don't have a link to each other. They only are linked to a common class. So we keep the coupling low. Cohesion also helps us to keep the coupling low. If we keep, let's say, the API, the payment stuff together, so that we don't have, oh, wait, to get the bank account or to get a payment stuff, I need to call this service calls another service. That also helps us to make stuff like easy to understand or easier to understand in our brains. And the other stuff is also that it helps us a lot if we reduce communication within our modules. We can communicate within the module, but not all over the modules. If we do that, it makes stuff like debugging easier and also increases performance. What you also can use for this, if you're in a more distributed scenario, you can use brokered like message brokers, the message size. We had this good talk about RabbitMQ lately, which you could use to exchange messages. or you can simply say, look, my component offers an API, be the REST, GraphQL, gRPC, or whatever, and the components can talk to each other over that given contract by the API. As those are fundamental things, I would highly recommend you to automatize that architecture stuff and enforcement early on. I mean, if you define it, there are tools for, I just put in some of, like ArcUnit is for Java, .NET has a port for that, PHP Arc and ArcUnit Node for Node.js. They basically do the same. It's like writing a unit test, but for architecture. You basically say in this class, let's say if I'm in payment class, in payment context, every class needs to have payment in the beginning, and they are not allowed to interact in certain ways. They are not allowed to go directly to databases and so on. These tools are really cool. In my actual project, in our core team, we used it now. We fully automated the ArcUnit with ArcUnit. It's a Java project, and the code review discussions we could reduce by 80%, because it's clear. We inserted in our CI/CD system. ArcUnit runs like unit tests. It breaks. If it breaks, your build breaks. You cannot check in or you cannot merge. Pull requests will not be allowed. So it's very easy to here reduce the cumbersome code review stuff. This is an important thing, and we will have that concept all over the talk again. Are there questions to this one? No. Then the infamous big picture. So what I always say in my course, software architecture is different from software development in mostly the aspect that as a software architect, I need to respect and follow the big picture, versus as a developer, I want to have or to solve a given problem in the best way possible. Now we have a problem because the customer usually comes and wants this one big system. And it could be that the solution of a certain problem, or the best solution to a certain problem, would give us a small advantage, but in the end, the homogeneity of the system would terribly get lost, or it would be very hard to integrate this small part into the big part. So as a software architect, the big picture overrides, in certain cases, technical optimal solutions. That means it could be that you will have to discuss, and I had these discussions quite a lot with people, to tell the developer, hey, look, this is not how you can do it, and we have to use maybe a not so optimal way or not so optimal technology, given that in the end we can create one big system. So this big picture thinking as a software architect is very, very important. Very important is also we are creating the technical vision of the company's product. So if they say we want this, we are the ones that design the technical solution of their big vision. And for this, we need to talk. And that's something as well software architects are usually not known about. If you tell someone, hey, software architecture, people will think about, yeah, techie, cool, now I can do like these arrows, and we call that boxes and arrow things. I can draw all these cool diagrams and then tell the developer how it works and stuff has to be done. That is a part of it, but unfortunately, it's maybe 40, maybe even less. The bigger the company, the bigger the project, the higher type of architecture you do. Like we have the technical architecture, doing a sub problem or a single application. You have a solution architect or a system architect, which has a certain system. You have a solution architect, which overlooks the whole solution. And then you have enterprise architects, which even like do the architecture of all the system in one enterprise. And if you're at that level, and I at the moment do deputy or have partial task, that is, it's all about talking. You're spending all your times in meeting and notes and Confluence pages. That's what I can tell you. So as a software architect, my job is to talk to people because I need to technically realize the functional vision of my customer or my product. And for this, I need to understand it first. So if you create a requirement process, you have usually a BA or requirements engineer, someone that tries to gather the functional requirements. Even there, it is very important, in my opinion, very important to have some techie, or in this case, software architect, working together, because at this point, they always can say, hey, look at now, this is a cool feature, but it will be very, very expensive. I mean, if you have that, if you have a very good expertise on your domain, or come from a development program, you can already say this is very, very expensive. That will be a lot of work, and maybe already at that stage, the customer can change requirements. Maybe they don't. And then you say, okay, good, then we need to take this. Also, it's important to gather information about the stakeholders that work in a project. In a project, you work, or in a software system, usually you have business people, you have management people, you even have C-level management people, you have infrastructure person that hosts IT people, and you have your developers. But all that together is necessary to create a successful software system. It's not, if you have a customer and devs that do not understand each other, there is this very infamous picture with the swing. The customer wants this, and then you see all these pictures of what happens, or people understand. And that is very important. In the end, you as a software architect are one of these liaison elements that the customer gets the software that solves the problem they want to. It could be they do not understand software, but they have they understand their business and how it should work. And you as a software architect are technical, like, realization person of those. So it's very important to understand the stakeholders. It's also important to understand the skill level of that, the tech skill level of a stakeholder, or the position, and what they expect from a software architecture. Why? I had this as an example. I was brought into a project, and this project was basically made to eliminate a whole department, which automatize and eliminate like 50 people from a company. To understand the processes there, I had to work together with those 50 people very closely. As you can imagine, basically they knew as soon as I finished my project, they lose their jobs. So it is quite hard to get information from them. And what I usually do is here, I make a little matrix internally where I list all these stakeholders, I list their roles, I list their phone numbers, contacts, and so on, and also their skill level. Because if I need to talk about a problem, a technical problem, if I bring in a class diagram with someone that has no technical background, let's say it's a hotel manager, they build a hotel POS system, and I come and show them a class diagram, this hotel manager will not have a clue at all. They will say, whatever, a lot of lines, a lot of things I have no clue and never seen. If you can create your architecture in a very speaking way, say here we have like POS items, we have products, we have an inventory, we have maybe drinks and food and rooms and cleaning services, all that stuff, you can discuss with them on a level that they understand. So it's very important to understand the skill level and also their, let's say, attitude towards the project. Are they supporting it, or are they reluctant to the project because it could make them get their jobs fired? The other thing is you have a dev team, the techies, and you will be supporting them. I mean, hopefully you will be. The worst what could happen is we call that ivory tower architecture, you define something and then you let it go to the devs and they do something else. I can tell you, if you do it like this, it will never align. At some point, these two diagrams at the end will never look the same. I mean, that's just because people need to exchange, and it is important that you also explain architecture and maybe as these big picture decisions already to developers, so that they understand why a certain thing is as it is and why they have to do it like this. It's also, in my opinion, important that these people understand why they're doing it. They need to understand the software we build is what, and why does the customer want to build that software. That helps a lot and gets people much more involved. The last point, periodically review the architecture. I worked in big companies. We did laboratory devices for medical use. So what we did is every year we made 1 week a software, like an architecture and a software review, basically, and we still checked, is the software architecture and the system still aligned with the company's visions. So they gave us a goal, and that goal was basically written down at the beginning of the project in several words, and we then checked if we are still aligned. Are we going in the right direction, or is the swing the customer wanted still becoming something really fancy but completely unusable in that context? Are there questions for this? So as you see, we are a lot into people and talking and documenting. Okay, so to get that, we need to ask a lot of questions. As I said, the ultimate goal, we need to write it down. I would really recommend to do that extra work. Write down in 3 to 5 sentences the main feature of the software. Like, when everything goes wrong, the software needs to be able to fulfill those features. The stakeholders I talked about already, and then we come to something that as an architect is more than into this techie position, the non-functional requirements. Usually a requirements engineer and the business analyst, they talk with the customer about functional requirements. Often customers say, hey, we have a cool idea. I had that in my past a lot. They say, look, I'm a hotel manager. I have this idea about a cool POS system or a property management system. I want everything be integrated. I want the customer to be able to report that they can choose from Netflix and Spotify, like in a dashboard on their TVs, for instance. They do not understand nothing about technique. And we as software architects are the ones that have to ask the questions to get those technical use cases. For this, I usually use something that's called a quality scenario. What is this? The quality scenarios is like a requirement or a user story, or no, it's not a user story, it's a requirement that defines required quality attributes. The trick here is that in those attributes, we usually try to include some kind of metric. It must be measurable. Why? 2 things. First, especially slow and fast can be very subjective. What is fast for you can be slow for another person. What is fast for another person can be slow for person 3. So if you here write in clear times, clear things, it makes stuff much easier in the discussion, especially in later stages with the customers. Oh, I want, this is not fast, this is slow. And then you say, no. At the beginning of the project, we said this, in the medium, the system should return 100 data records in under 600 milliseconds. If you can prove it with 100 milliseconds in 300, 400 milliseconds, then they cannot say nothing. I mean, this discussion ends here. They can still try to change it, but then you have a leverage to tell, okay, but especially in our outsourcing world, but you are aware this is not warranty work or we did nothing wrong. It is just your expectation that's changed. So for us, that's very important because we then can claim the extra work and do not have to warranty work if we do stuff like this. So make sure that your quality scenarios, they are defined in numbers. Here as well, the system assessor should be able, a million complete total users, 280 concurrently, and the system load should not go over 80% then. This is important for you, architectural decision. Do I need a Kubernetes cluster? Do I need a Raspberry Pi? That's like basically your technical decisions, which help you to build that system. Also, this here can be tested. I mean, depending on how extensive your testing is, or how, the knowledge of your optimization degree here, it helps you a lot, because these are, as we said, here we have numbers, so we can write a load test for this. I mean, I can simulate a million user, I can check the load test, and if that goes over in a CI/CD system, for instance, I can run those tests once a week, once per 3 days, and if one of those metrics fail, I immediately send out warning, break the build, do whatever, and say, hey, the things we did between this and the last check made the system not be compliant anymore. That can be the reason, and have good reasons, and say, okay, good. In this case, you will have to discuss with the project manager, project sponsor. Could we maybe say it's now 650, or can we change this to 700? So what you do is you document this afterwards, say 700 milliseconds. We increased it to 100 milliseconds because of X. And also in this thing, that's like if something changes, management changes, discussions come up, bad blood comes up here, you have a number, all the people did agree on, less discussions, and you say, look, this is my system, and it proves that it's faster, or it is compliant to those quality scenarios. I would say make around 20, 25, maybe 30, but not more of those quality scenarios, which can help you a lot in building your software and making technical decisions. Are there questions to this one? Okay. This is for cloud systems, as I gave last week a talk for our colleagues in Lithuania, and that were some questions that came up. If you do cloud system, I think there is an extra factor. So because you have a cost factor, you can do a lot of stuff in a lot of ways in clouds, but that costs money. And if you have those things, so ask, hey, where are we now in 2 or 5 years? You can also ask this for a normal system, not in the cloud, but if you have cloud-based system, this can be cost affecting. Do the users come in waves? Are they steadily? Are they working 9 to 5? Are they 24/7? Do we have to expect from 100 to 1 million users, or what is it? So you can choose, do we need a Kubernetes cluster? Can we do it with single Docker containers, cloud instances? Do we need a serverless or whatever? The other thing is we have a lot of European customers. Are there any compliance restrictions, such as GDPR, regulatory ones? If you are working in airspace, like space technology is the worst. You just write one line of code and 100 pages of documentation for that one line. But if there are regulatory things, these data is not allowed to be in that country. So just ask these questions as well, especially in cloud scenarios, as you have to choose region of your services. In the end, that's something, if the customer, often it's a software as a service thing, has a, they ask for a licensing model. So they should give you a targeted cost frame, especially in the cloud system, because what you then have to do is you have to calculate your solution against this cost. If your best solution works cool, but costs $10 and the per month, for instance, and the customer comes and say, hey, my license cost is like $5 a month, you have a problem, because you're already with one feature $5 over there expected cost. So you need to respect those cost things. And the other thing is, if you go to a cloud, depending on how far you integrate into the cloud service, you get a vendor lock-in. And for us as software architects, it's very important to understand, do the customer accept vendor lock-ins? Then we, for instance, could go serverless, or can use in an IoT thing, the stream-based. We can use the service bus made by Azure. We can make those cloud services. If they say, no, we want to be flexible, so maybe Docker containers with a Kubernetes cluster are more flexible and portable to another cloud or coming back to on-premises. So they all work. They also work, like these questions also do work for a normal architecture, non-cloud architecture. But if it comes to the cloud, I would recommend to always ask that question, write them down, because otherwise, I mean, if you make basically software architects make the most expensive decisions or mistakes in a whole software system. So let's say you fuck it up here in the cloud initial configuration, you need to change everything back. That costs a lot of money. People will be angry. If you write it down and have the customer in the end sign it off and say, yes, agreed, then you are still getting a lot of blame, but it's more safe than what you do now. Are there questions for this one? Okay, so let's come to the architectures itself. First, we start with something a lot of people think is stupid and not cool anymore, a monolith. In a monolithic architecture, we have one delivery unit. Everything is together and handles all the aspects of an application system. Now, a lot of people come now and say, oh, no, monolithic is bad. I don't want monolith microservice all the time. I say, depends. You can hardly beat a monolith in terms of speed of processing. I mean, this thing is one class, it is in process, in memory. Basically, I can shift around data as fast as possible. I can do computations as fast as possible. So if you have something that needs to compute really fast, you will have a monolith. I mean, if you go to let's say you have a production machine thing, a production system, where with the conveyor belts, they fabricate car parts. I mean, those machines that check something, these parts that do check something, they're a monolith, because they need to have basically, they have an image, and within 20 milliseconds, they need to decide if this part according to spec or not and sort it out. And in this case, a monolith will not be beaten by nothing, because everything in process, everything in memory, and nothing can happen. So if you have that, a monolith is nothing bad. And especially if you have something which is called a modular monolith. I mean, we have solid principles. All of you should know that as in the technical role. We have these design principles of solid code. And that means if you accept them, you still can create and use things as dependency injection. You can still use stuff like a segregation of concern. You can have stuff like interface segregation. That's nothing that cannot be done. And if you have a well-done modular monolith, that just means you can only deploy everything at once. But you still can have one team working on this, working on this, working on this, working on this. That works. It just in the end gets deployed as one. The evil twin here is the monolithic big ball of mud. But if you distribute the stuff, then you even have a distributed big ball of mud, which is like this times 100 million, because then you're really fucked. But I mean, people often think monoliths look like this, but if you do a good monolith, it can be a massive gain in speed. Are there questions? Okay, so coming into monolithic architecture, coming from a monolithic pattern here, the layered architecture, I think this is something a lot also monolithic architecture or systems look like. In a layered architecture, you basically split a system into several layers. Every layer holds a specific task or set of tasks, and those layers basically call each other. We also should try to achieve a loose coupling here. So we can use dependency inversion, dependency injection, we can segregation of concern, and contracts and everything. So basically, what are we do mostly in those systems? You have a presentation or communication layer. I mean, if you don't, this is a desktop application, so I have a presentation layer. In an API, this would be the API controller where your calls come in from here. Then you have a business logic layer that handles the data. It transforms the data and understands your business domain. What should I do if I get, let's say I have an input 1 and input 2. So the business domain does know how to handle those inputs and what to give back. In the third level, you have a data access layer. The data access layer knows about where data is stored, how to access data, how to retrieve data from the storage or from an API and provide it to the business logic. So this, I think every one of you knows, this is like a lot of, let's say, legacy systems, well-designed legacy systems look like this at some point. If we go once further, we have those group of architectures, which is called onion, clean, hexagonal architecture. There are several names of this. They basically also based on the layered architecture. The idea here is they segregate it more. So if you have here only 3 layers, here you have a lot of layers. You see, it looks also more complicated. What they do basically is they say, we have a core or domain layer, and this thing that changes not often, because this is basically how a process, a business process works. For instance, we had this in my project before. We did liquid handling system. So basically we did blood. You put in a blood sample and it does analysis on this blood sample. The analysis on that blood sample, the test it does, and how do I measure the data that comes in, that's always the same. That's the given algorithm. I cannot change this. I mean, I don't care if this data comes in from a camera, if it comes in from a chemical sonde, if it comes in from, I don't know, a picture, someone can send in whatever. The method to process this blood sample image is always the same. That does not change. And then we have like external stuff, which can change. The UI, for instance, the API. Maybe I say, okay, I have now a mobile app and I need to change some API interaction points. In the end, my domain layer stays the same. I do blood analysis, whatever, but it can be changed. It can be an API. Maybe it is only a desktop. It may be that we have a web version suddenly, and we have to explore exchange data now. We started with an Oracle database that became too expensive. We use a MySQL now. And we can ask about patient data, maybe. In the early system, it was entered manually. From here, it was manual. And then now we have a data patient exchange system. In the end, our domain layer does not care. So that's exactly what this onion architecture are. We have the domain layer, and then we have something that they call an architecture, an infrastructure layer. And that infrastructure layer is then connected via something that is called ports and adapters to the outer world. We try to abstract all those layers from each other. That means exception, they have their own exception handling, they have their own data retrieval, their own unit tests. And this here, the inner part never knows about the outside world and does not care. The domain layer, in this case, the blood analysis, they don't care if that patient data is retrieved from a file scan, from manual entry, or from a third-party system. They say, I expose as a port my patient. The patient object must have name, first name, last name, age, gender, and maybe some vital data. And as long as you fulfill me that object, However, I don't care where it is. I can work with it. The same from the blood sample. I mean, if that can be done by a laser scan, if something externally processed it, or however this is processed, as long as the data comes in the format I say my port exposes, I don't care. The same here, and if I want to save data, I inject, and that's the dependency injection thing. So I say, hey, I want to save data. And where I save that data, I don't care. The outer layer here, they need to care. They need to know, okay, she wants to save data, or he wants to save data. So I have to access this MySQL database with this username and so on. The domain never knows. They just say, hey, save this data for me. The same is when you do it's for you, it's the same as if you do a grab. I mean, you don't care if your Grab driver drives a cool bike, a small bike, whatever, a big bike. You also don't care where exactly the Grab driver goes. You just give the product to the Grab driver and says, thank you, handle that for me. And at some point, the Grab driver or marks in the application, hey, it's done. So you know, okay, this process is shipped. So for you, the world did not change. So you can, for instance, if you make sausages or sell sausages, you don't care the way these truck drivers drive. You don't care if they transport it in one box, in a backpack or whatever. You just say, hey, transport this from A to B. And this is a very important concept and helps you a lot, because if the customer comes and, hey, we want to exchange this, or we now have an API, you don't have to change this whole system. Saves you a lot of unit tests. And if you're, like in our case, a blood analysis machine, that means full validation, FDA bullshit, millions of dollars you would waste to just exchange something. If you do this via this adapter and this port, you can say, okay, because like sometimes you can get away with this, because only this changed here, I only have to retest and revalidate this. Costs me maybe $50,000, still expensive, but not millions. So make sure that you can abstract those architectures, and these onion architectures, hexagonal clean architectures, they all have this core layer, infrastructure layer, and this port and adapter communication with the others. Are there questions for this one? Okay, as I said already, this is like just a recap again, abstract the layers. If you have a layered architecture, if you have an onion architecture, make sure they use contracts, they use interfaces, dependency injection, and make sure that the inner parts never know about the other parts and do not care. If I want to send something over a network, the use case at the end, the core module should never know how it is sent. If it's sent via TCP, via UDP, whatever. I just say, send me this grab principle. I give you the sausage, say grab driver go. And the grab driver goes and says, hey, I delivered it. That's how it should be. I don't care about the database. And I also do not want to care about a database specific error. Let's say this is an SQL error. I don't care. My proxy or my port here needs to handle this. They need, as a repository or proxy or whatever, they need to check. If they say, okay, this is an exception state, they have to use an exception that comes from your core or from the underlying layer, and they have to throw that exception. You should never handle a database exception in the core business, in the core business logic, because that makes you basically, again, coupled to it. We want stuff stick together, but we want it loosely coupled to external stuff. So I don't want to care if this is a Windows, a cloud, or a Linux system. I don't want to care about database type. I don't want to care about network. So please abstract the layers and you save a lot of work. It is a bit more work to write, but you save a lot of work when shit hits the fan or stuff, changes like this come in. You just have to adapt a small part, and especially in validation and high risk system, that saves your ass by like 90%. The next one, MVX Viper architectures for the front-end desktop people, mobile people. MVX architectures and are often used in desktop application, in mobile apps or web application. Like the MVX is like the MVVM, MVP, MVC. They all basically work the same. You use it nowadays in mobile application like Android as an MVVM model, which they provide in iOS. It's called Viper, view, interactor, presenter, entity, and router. So basically but they always work basically the same. You have a view. The view handles all visual things. How the buttons look, where the buttons in the page are. They also handle like visual animations that don't rely on data and all that fancy interaction and shiny stuff. I always say this is the makeup of the application. And then you have something that is basically a presenter here, or the view model, or the controller, whatever you call this in the end, something that has the brain. And the brain basically communicates to the view via a binding. I say, okay, this in my text box, I display the text which the presenter or the view model gives me. Why do we do that? Mostly it's testability, segregation of concern and testability. Because the biggest problem was it's very hard to test view elements because they have a lot of properties which you would have to fill, and it's very hard to mock them and set them up. Everyone that ever used the coded UI test knows how hard it is to write these coded UI tests and make that. It's a lot of work and a lot of pain. So I want to check basically every interaction without ever seeing the makeup part. I want to have the nude application. That's done by the view model or the presenter. Here, basically, I can every interaction and every state change of a method, I basically can simulate via unit tests here in the view model, because this never does depend on really the UI elements. It's pure code. So for this, that means I can write a good unit test, and I basically could even do integration test without the view. And in the end, my human test person only in big brackets has to check if the animations are correct, if the layout is correct, if the buttons have the correct color, and so on and so forth. But function, I can check. Then we have something like called a model, or here interactor entity. That's basically where the data comes from, where in a monolithic desktop application where the business logic is handled, that's your core. And at some point it talks to this view models or this presenter. So here is also the brain that calls like to the database. It can call to an API or whatever data transformations are needed. Basically, here we are in the deep brain or in the deep business logic, domain logic. If you have an application that is only consuming data from a backend, mostly the model here are something like state. It basically calls the APIs, calls the backend, and provides the data from the backend and gives it then to the view model, which then gives it to the view. Are there questions for this one? Okay, that were mostly systems that worked as one together, MVX for desktop, layered systems, and so on, often come in monolithic one. Now we come to the distributed system. In the monolithic architecture, we had everything together, these layers. In the microservice architecture or a distributed system in more general ways, we start to split that up. Here, I need to, because it's one deployment unit, one DLL, one executable, whatever, I need to deploy all at once. So if I change a business layer and the user interface is 2 months late, then I have to wait 2 months until I can deploy this. So if I go to this microservice or the service or distributed system, I can say, okay, my business layer is now faster. Maybe because it does not break any UI stuff, we can already deploy it, and the user interface can already use the new business layer. So you start to split up those business function logics into smaller parts. It's cool because it can be easier updated. It can deploy partially. Several people can, several teams can work on several services. It sounds like the coolest thing ever. Yeah. Yes, it sounds cool on paper. Honestly, I do not know many companies. I know some, and I worked in projects and big companies like Netflix, Amazon, or so, they do that. But honestly, a lot of the people I know do not deploy partially, and do also not really come into the thing that they update parts of a system, and that's the contra that they deploy and really work on this microsystem stuff. There are companies that do that, but I say the mid-term startup people usually don't do that, simply because they don't have a lot of people that can work on this. The other thing is distributed systems are a nightmare to debug, because something happens between in here. I mean, this is an easy one. Could be that these start to talk together to each other and so on. If you debug this, I can tell you, you need 3-4 times more time than if you go here and say, oh, I set some breakpoints, one interface or one executable to rule them all. I debug here. I see my jump points, where it is, stack trace, everything good. Here, oh, wait, this one worked, or maybe this one fails. And if it's bad, this one fails only every 10th call or whatever. So debugging those are hardcore to debug. Like, it's really bad. And also, they have something that's called the 8 fallacies of distributed computing. I don't know if you know this about this, but I fell in all of them. What it is, basically, it's like 8 things that someone, it's a Java, someone that was in the Java team of Sun, they said something everyone falls into. And that's like these things. They say the network is reliable. So that means every of those microservices reachable all the time. I mean, we all know, no, it's not. Latency is 0. If I microservice here calls this microservice, that's immediate response. We also know that's not true. We need to serialize it here. We have a protocol with overhead, be it HTTPS or so. We need to decrypt it if it's an encrypted protocol, deserialize it, do something, serialize again, create here a new response, overhead, and so on. Latency is never 0 and can, in small calls, take more time than the call itself. Bandwidth is infinite. Also, I mean, that can, it's in a cloud thing, it can be bandwidth is for free because it's not, depending on what you do. That can be a significant cost factor. And also the bandwidth is not infinite. It can be slow. Calls here can be slow. Network is secure. We put stuff in a cloud. That's basically in everyone full control situation. So we need to secure the system. Then the topology, that's not so, these come from 1994. The topology of the network does not change, but it's still, I mean, routing can change, router can change in distributed system. We are prone to that changes. There is one administrator, or the administrator knows what he or she does. Often that's a problem. You have microservices, the teams have also several DevOps people, and A and B do not talk to each other, and then you already have the issue or the more work to do. The transport cost is 0, meaning the cost between those two, if you use a protocol like gRPC, if you use a protocol like HTTPS, SOAP, whatever is there on the market, they have more or less overhead. But if I send 100 bytes, maybe the overhead is 1 kilobyte. So 10 times more, that can be. So transport cost is not 0. And the network is homogeneous. Never the case. I mean, you have routing tables, you have firewalls, you have stuff that does not work. So be aware of those fallacies of distributed computing and keep those in mind if you do it. it could be that in the end, you split something up that's slower than this one, much slower. So be aware if you need speed, and in the functional requirements or non-functional requirements, sorry, in the quality scenarios, we define speed, and we see we cannot reach speed in this scenario. Rather go to a monolith than split, or to a macro service, we call that, not a microservice, a macro service. Say these three together are now a monolith which handles it, but I have maybe 10 such monoliths which are macro services and not microservices. Good. Distributed system patterns here. Gateway aggregator. This is, in my opinion, like most of the gateway, like the cloud apps especially, should be built. You have an API gateway, you have a client that consumes that. The API gateway authenticates against an IAM system. As you see, this is internet, and this then forwards the calls to the backend services. That can be single web apps, Docker containers, it can be Kubernetes cluster, can be serverless, whatever. But basically, they are also in a private network. They never see the internet. Their firewall rules do not allow to go from this part to this part, never from pink to blue. They cannot do that. They always have to ask the API gateway. If they want to communicate like here in this pattern, they call the API gateway, and the API gateway goes back. That means you lose a bit performance, you gain a lot of security, because it's not easily, like none of this client can hack directly here. I need to first get access to this pink network, private network, to gain access to these services. So this is a lot of security you gain with a little thing. Every cloud provider offers that. There are also on-premises API gateways that help you with this. Even Kubernetes has special ingresses like Kong or so that can do stuff like this. It also pre-authenticates your calls in an IAM, like an identity and access management system. This is mostly just relevant for situations when you have cost. If that costs me the execution, someone tries to bugger me here, and I say no, then I never reach this service, and to keep the cost low, because here usually it's a monthly fee versus a per call fee. The next one, the message broker, works the same way as you saw before, but instead of the services asking the gateway where they put messages on a message bus, we had the call last week about RabbitMQ. So you can use, for instance, a RabbitMQ. We put a message here, someone else calls, takes that message, does something, sends a new message here. That's how these event-driven systems work. You use a message bus and you send events, and those listen to each other. This is a very good way to lose a couple things, because I just send a message, let's say user created, and someone had some other services, or maybe also no one listens to that, and they can work with those data. So it's a very good thing to decouple services, and it's also quite fast and reliable, as you can, these message bus can also save the data persistently. If the system goes down and comes up, you have the same state. The problem with this is the bus system is a big failure point, so make sure that you have a infrastructure that have a failover thing or whatever, so that in case this fails, nothing would work anymore. So you have to have some failover or some disaster recovery, and also make sure that this is secure and that you have the information persisted. If it goes down, that you don't lose any information. So almost at the end, service meshes. This is something mostly used in Kubernetes scenarios or Docker scenarios. So what we do is we say we only focus on the codes, like our core works only with code, and for everything infrastructure, I call a proxy. The proxy handles call other services, keep stuff in state, save something to the database, whatever. I just say save it, the proxy does that. The thing is called a service a sidecar, because there is a methodology in like a sidecar. For those who don't know, you have a motorbike, and the thing is attached to the motorbike is sidecar, so you can have a second person sitting beside you, and that's exactly how this works. the Docker file can glue this together. So this is like one Docker container or one pod. It is considered as one pod, and the service just connects locally to this. So this sidecar proxy usually is then handled or defined once and configured by either infrastructure team, a mixed team of devs and infrastructure. And for me, I don't know even where this sidecar will save my data. If I say save this person object in my proxy, it could be it saves it to an XML file, to an Oracle database, MySQL, Postgres, I don't care. I just say save. And all the logic of this infrastructure configuration here is handled in a sidecar. I glue them together when I deploy them to a cluster or whatever. And then basically this focus just on code. This is cool because you can have a pure dev team and some infrastructure DevOps team, and they are not blocked by stuff here. They just say, I send it here and something happens. So this can be cool if you have a changing system, or if you have something with a lot of function, a lot of proxies with a lot of components which need to have a homogeneous communication. This is a good pattern. There are Istio and Dapper, I think the most common on the market for now. Then the last one, as we're running a bit late already, I'm sorry for this, Lambda Kappa architectures. This is mostly used if you have to process data streams such as in IoT, big data, machine learning stuff. Those architectures work, it's basically the same way how they work. I have a data feed coming in that can be IoT data, it can be, I don't know, camera images from like your parking systems, like makes a camera picture, and this camera pictures checks let's say the model of your bike and your license plate. Because that needs to be fast, we have one speed layer. In that speed layer, basically we access everything is cached. We have a fast transformation. We say, okay, this person is registered in our database and can enter our parking space. Maybe in a Lambda, this is the Kappa architecture. Data feed, one speed layer, showing everything or doing everything. This is Kappa. And now with the Lambda, we get another leg, and that's a batch layer. Let's say in our example, we want to know how many people from which province, which motorbike entered. I want to see this month, I don't know, 100,000 people entered, 20,000 Honda, 50,000 Yamaha, and 30,000 Suzuki. And they came from province, I don't know, Ho Chi Minh City or from whatever. So I can do that by the first two numbers of the license plate. Because this is not really fast and does not need to be fast, we can use the batch layer where we store the images here. Here we immediately process it, say, access, open the barrier, and people can go in. But here we save that data, we process it maybe every day, once a week, and say, aggregate all the license plate number, aggregate all the models and makes from the bikes. And in the end, every month, I get that information. So the Lambda architecture has this slow layer and the fast layer, and the Kappa architecture just have the fast layer. In a machine world, usually the Kappa architecture is if I don't do predictive maintenance, if I don't want to know about special parts, I use just a Kappa. And if I have predictive maintenance, let's say I want to send an email to the owner of that machine. If we find out that we did this for coffee machines for Starbucks and McDonald's, that's a lot of machines. So they find out if their machine parts start to get word of their service department gets the mail, and then the service technician comes and can fix it before something happens and the machine is broken and stands still and they cannot serve coffee and lose money. That's in a big thing for Lambda and Kappa architectures. So that was it. I'm very sorry it took me a bit longer. Are there any questions from your side?
All right, so I have some questions from Slido, but I think because we're running out of time, so you're gonna pick 3 out of 5 that we have
Yes,
here.
just a second.
Sure.
I just need to open it that I can see this. Here we have this one, huh? Slido. Here. Oh, now we have more questions. I do not take the dependency injections question. I think we handled that already. Opinions of PHP, we can do that at beer. I think we are on the architecture. Architecture should be technically agnostic. So, but I happily discuss PHP. Yeah, maybe when customer doesn't care about software architecture and just wants to have the feature as soon as possible, how would you carry out the development? I would like the first thing is write it down. Make a decision paper, something, write it down. And if they don't care and don't give you answers and stuff, and you need to assume stuff, or you take a decision, but you're not super sure if it works or not because you do not use the time to have the architecture. Write everything down. If you write it down, confidence whatsoever, and then send it to the customer and say, look, customer, this is how you want to do it. You omit everything. Also, if they say we don't want testing, write it down. And if something breaks and they get the shit, then they will come to you. Why did you not do it? Blah, blah, blah. You're bad, and so on. And say, no, sir. Here, this is exactly what we agreed on, and this is what I did. You said this is okay. So write it down, and then I would try to still. I mean, I still would maybe not make the big picture with all the stakeholders and the vision and reviews and everything, but I still would create a diagram for the development team where we even sit together or do it yourself, but they communicate to the development team, which we have a overview, which parts of our model are there, where are external interfaces, what do we have to talk with, and so on, so that we still see at least a little hand-drawn drawing of our system. I have a little e-paper pad, and I usually draw with customers stuff like this in either my enterprise architect or on this. Like I did this with Torben when we had an estimation for a customer. So we try to get a big picture of what we need to do. When there is no software architecture in the team, which could result from a customer's budget, what you suggest the team to do? I suggest sit together before. I mean, you have a ramp up phase if you have a new project. Sit together and discuss. If it's a big team, maybe do it with more leads, but to make a prototype, but discuss it in the whole team. In the end, the whole development team needs to work on the system and needs to have the decision clearly communicated. If you are a team of, let's say, 4 or 5 developers, sit together. It takes 2-3 hours and create this diagram of the arrows and boxes that at least you see, hey, this is our system. We go from here. We have here, let's say, a shop. We have products. We have orders. We have payment. We have users. Here we need to have a IAM system, like a key cloak. Here we have their ERP system, so that you see what is there, what is around, and do this together. And then I would say, I mean, there are 2 things. Either you say, the whole team that does these decisions together in ongoing work, if the customer is okay with that. Or what we also did is we said 1 or 2 sprints. One person has a software architecture partial role. So you say, okay, to this sprint, we make it 2 sprints. Person X has the software architecture hat on, and they are required to make the code reviews in a way that the software architecture is respected. They need to have the documentation ready and all that stuff. So you can say, we call that an architecture agent. We had that also in projects where we had like a lot of teams and it got really hard to get everyone involved. So we had like 15 teams, around 100 people. So we made these eight software architecture agents, and we came together like in a scrum was a scrum of architects, and we discussed architectural points there. And then we go to the next one. How about using GraphQL instead of API gateway? These are two things. So basically, the pattern is that the GraphQL is a paradigm how to give data. An API gateway is an infrastructure part. So the functionality, I would say, the API gateway functionality in the GraphQL are similar. But in GraphQL, basically, I deploy, I ask my data and give it back. I mean, yes, you can do this type mapping and everything. The thing you will have to use this reduce function. Is it reduce? I think it's called reducers in GraphQL, and then they go to the end system, and that's what how usually I also do with the, an API gateway can do part of that, but basically you can do GraphQL or REST or gRPC with an API gateway. In Azure, I'm just knowing it from Azure. Azure API gateway can support a GraphQL API. The API, like the API paradigm, is a GraphQL or REST, and the API gateway just helps you mostly here as a infrastructure part to keep those going. I mean, the API gateway also helps you because it does scale automatically instances if needed and have this automatic integration. You can do this with GraphQL as well. You can do this with a REST API. I mean, the business logic could also do that. Most of these REST frameworks can also do part of this. I would say for me, the API gateway is an infrastructural part or a system, and the GraphQL is a paradigm which shows me how to access the data, if that answers the question. The good patterns for caching architecture. Basically, what I do mostly is I have two caches. I have a read cache and a write through cache. A read cache is basically I just read from this cache all the time. If the value is not there, I go to the end system. That's the easy part. The not so easy part in this system is how do I synchronize it? Because if I save something, because usually in a read-only cache, I save something to a database data storage, and at some point an event, message, or whatever, it get notified to update or invalidate the cache. And this time, the next read could read some stale data. So that's what I prefer, is a so-called write-through cache that works like this. I create a transaction. I write first to the cache, and if the cache is correct, if the cache write worked, I basically then forward the call to the slower data storage. That means when I saved it to the data, when I saved it to the cache, the next read will have the updated data already. And as the cache said it's okay, and I update the database, then they are easier to sync. It still can fuck up. That's like the thing we need to be aware. If the transaction to the database, as the database or data storage is the ultimate source of truth, if that does not work for whatever non-technical reason, if it's functional, I did save something wrong, I would have to roll back this, and you would have the stale data as well. But I usually prefer these write through caches, so I write it first to the cache and then to the slower storages, so that the data is as updated as possible. Good architects need good resources to implement. No, that is partially true. good architects should be able to understand what resources they have and build a system that also includes the skills of the dev team. I mean, if you have a dev team with just juniors and the customer wants a crazy complex team, I expect from you as a tech lead or senior to say, hey, we have a discrepancy here. I mean, this will not work in time or budget for the customer. It's much too complicated. These people do not have the experience. But if you have a system in customer scenarios like ours where they buy a team, this is a bit different. If you work on a product for a company and they come and say, hey, look, we want this crazy complex thing and we have all these developers. I had that once. They came, hey, we make now a C# application and I have 50 Java developers who never coded C#. But they will do that and I will be able, and should be in like 3 months done. And I said, forget it. I think this is something you have to take into consideration when you talk to the stakeholder, make the stakeholder list in an architecture, because that also says, I mean, their skill level of the development team is maybe I have 20 Java developers. Customer wants a .NET app. Maybe something's wrong. Or I have people with extensive PHP knowledge. Customer wants Ruby on Rails or C++. That could give some discrepancies. So if you can make the architecture also fit the development team up to a certain degree, and if you don't have many resources or many good resources, then I think you have to track it. Like, it's not controlling, but I mean, then just maybe you need to be more involved into the development process, maybe code reviews. I strongly, then, if in exactly this case, I strongly recommend you to create a CI/CD system to use this ARC unit or these architectural unit testing language. It's maybe hard to tell like this. So also less experienced developers, they fail early. So I mean, if they make a pull request fails because naming is not correct. If you say we don't save data, we save data not directly but use repository, and if those things are checked and the constraints are violated early on a build, so it gives me, I mean, I'm pissed. I need to deliver. It does not work. The first maybe 2 or 3 times, I'm super pissed. What the bullshit is that? Why does it always fail? Why is my build not working? And after that, I mean, I think people are these creatures of habit. They basically learn how to adapt to pass the check-in criteria. So if you have a less experienced team, I would say set up these rules more strictly. Use tools like SonarQube, include them in your build, Paragon, ArcUnit. I mean, automate that stuff. Automate also unit testing, automation testing. The more you can automate and the more it buggers you, like breaking your build, that's the thing that you can make sure basically that everything is mostly according to this. So if you have a good software architect, like a good software is a strange term, but if you're a software architect and your team is on a much slower skill level, I would try to automate a lot of things and tell these people immediately build breaks. So either they will leave or go to another company, go to another project, or they will just adapt and learn how to code within the rules, and then you have the quality you want. Are there any further questions? Or is someone's question not answered as well as they wanted, or I don't know, did not get the answer they wanted?
I think people can send you the message privately after this talk.
Yes, I mean, if you have more questions, just send it to via Slack or email or whatever you like.
All right. Thank you
Okay.
so much, Jane.
Thank you
for
so
the
much,
show.
and sorry for being a bit late and having overrun the time a bit.
Thank you, everyone. Have a good night.
Thank you. Have a good evening. Bye bye. Thank you.
Bye-bye. Thank you.
Somebody said the question in the chat, but nobody answered. Oh, thank you. Yes, it's time for drinking. Bye bye, em. Bye, Jimmy.